Next time you look out an airplane window, remember that inches away, raw physics is being bent to keep an inferno contained. At 35,000 feet, locked inside an aluminum housing just inches from 300 human beings, the fire inside a jet turbine reaches 2,000 degrees Celsius. That is 700 degrees hotter than the temperature required to turn that metal into liquid. By all physical laws, these blades shouldn't just bend, they should vaporize. Yet they spin for 20,000 hours without taking damage. They don't survive with heavy shielding. They do it by forcing air to act as solid armor. Here's the secret most people don't know. Jet engines use up to 20% of their own thrust power to pump cold air into the turbine blades before it ever touches fire. Air enters the base and travels through an internal serpentine maze, a 3D labyrinth designed to maximize surface area, so heat bleeds out from the inside. To escape, the air passes through microholes drilled at precise 15-degree angles. If drilled straight at 90 degrees, the incoming fire stream would rip the cold air away instantly. This angled release creates film cooling, an invisible boundary layer of cold air just 0.1 millimeters thick that coats the blade like a fluid blanket. Across a distance thinner than a human hair, the temperature drops 700 degrees. The raw fire literally never touches the metal. If a single cooling hole clogs, the cold air blanket ruptures, a localized hotspot forms, and structural decay begins in less than 50 milliseconds. Because film cooling can fail, engineers coat the metal in a ceramic barrier so advanced it requires 3 distinct microscopic layers to stay glued to the alloy. Underneath the ceramic lies metallurgy's greatest secret. The entire turbine blade is grown as one single, continuous metal crystal. In normal metal, microscopic borders between crystals pull apart under stress. To fix this, molten nickel is drawn through a spiral corkscrew mold that kills all crystals except one. Without grain boundaries, a single blade can hold 40,000 Gs of centrifugal force, the equivalent weight of 2 double-decker buses hanging from a piece of metal the size of your phone. The real nightmare is thermal expansion. Nickel expands twice as fast as ceramic. If locked together directly, the ceramic coat would peel off like old paint. The engine fixes this by growing its own glue. At high heat, aluminum inside the blade bleeds to the surface. This forms a self-healing layer just 1 micron thick. But this nanotech shield has a hidden killer, C-mass, a mixture of calcium, magnesium, aluminum, and sand found in atmospheric dust. At turbine heat, sand turns into liquid glass. It seeps between the ceramic feathers, freezes solid, and rips the ceramic off the blade in massive chunks. The instant ceramic flakes off, the raw superalloy behind it melts in less than 4 seconds. This happens under the 2,000-degree gas stream. As the tip melts, rotational balance vanishes. 40,000 Gs of force snaps the weakened blade, launching a metal missile into the spinning assembly. At 12,000 RPM, one broken blade triggers a domino collapse, destroying every turbine disc in 1/100th of a second. To protect the cabin, engineers wrap the turbine in a bulletproof belt of woven Kevlar and high-strength steel designed to catch supersonic shrapnel. At the same time, piezoelectric sensors detect the vibration shift, slamming fuel valves shut in 50 milliseconds, faster than a human blink. Modern combustors go even further. They shape fire geometrically, forcing the core flame to float in mid-air, so it never makes physical contact with the engine walls. During flight, internal acoustic sensors send ultrasonic waves through the spinning rotor, scanning for microscopic internal cracks before heat can exploit them. These combined engineering tricks extended turbine blade life from 50 hours in 1950 to over 20,000 hours today. It is a machine that operates inside a continuous explosion, surviving only because every single millimeter is designed to defy physical limits. Now, aerospace engineers are abandoning metal entirely, replacing superalloys with matrix composites that survive 2,400 degrees with zero air cooling. At Mach 5 hypersonic speeds, air friction alone heats incoming air to 3,000 degrees before it even reaches the fuel injectors. To survive, hypersonic engines route freezing liquid hydrogen fuel through the engine's skin, cooling the metal before burning the fuel in the combustor. These organic internal paths cut cooling air demands by 30%, instantly boosting overall fuel efficiency to record levels. 3D lasers are now growing turbine blades layer by layer, embedding cooling channels shaped like organic blood vessels. These paths were impossible to drill. This is the hidden war waged inside every flight, where a microscopic film of air and 1 millimeter of ceramic stand between safety and disaster. Just like thermal boundary layers keep jet engines from melting, extreme fluid shock waves determine how modern torpedoes break warships in two without ever touching them.